So continuing on with section 9.1, we had a few different properties of vectors. So if we had v was a vector, we could write it in that representation, or AI plus bj. We had the magnitude v, and we could have the direction theta. So again, the geometry looks like this: length v, direction theta. If we set it with an initial point at the origin, we have a terminal point, AB. And suppose we had a vector, say magnitude of v was 8 and theta was pi over 3. So we knew the direction and we knew how long it was if we want to find the horizontal and vertical components, so we can write it in terms of i's and j's. Well, from the last video and in your text, we see that the first component, the horizontal component A, the absolute value, or the magnitude rather, of the vector, times the cosine of the direction. So 8 cosine pi over 3. Cosine of pi over 3 is a half, so that just works out to be 4. B, the vertical component, is the magnitude times the sine. So 8 sine of pi over 3, that's square root of 3 over 2, so you end up with 4 times square root of 3. So V is equal to 4I plus 4 root 3 J. Now, what if I want to actually put together something that's modeled by this? If I've got things that aren't moving at nice 90-degree angles, everything perpendicular to each other, we can use vectors to represent some of these things. Sometimes you see things that are represented as whole strings of vectors. And really, if you're watching the Weather Channel or something like that, and you see, here's our map of Auburn, and they start showing you, there's the way the wind's going to blow, and we've got another wind that's blowing here and here. And oh boy, sweeping across the Alabama plain. And those are all vectors that they're using to represent it. They all have some kind of a direction. They all have some kind of a magnitude. A lot of times the direction is measured just by the angle it makes with some predetermined set of axes. But the magnitude frequently is how strong it is. You'll see this as a representation. The length of these vectors being used to represent maybe the speed of the wind, something like that, some kind of a force. You know, we could even put something in here. So suppose these are winds at 30 degrees northeast. So 30 degrees up from there. And the winds are blowing 40 miles an hour. I'm going to send an airplane due north at 300 miles per hour. Now the airplane is just going due north. So if I say that V is the vector for the airplane, it has no horizontal component, but 300 for its vertical component. So I could write it as 0I plus 300J, or 0, 300. But if I wanted to do the same thing for the wind, say I let the wind be this vector U, well, it's going to be 40 times the cosine of 30 degrees times I plus 40 times the sine to 30 degrees times j. We can evaluate these, and we end up with 20 square root of 3I plus 20j. But something that's kind of cool with vectors, how fast is the airplane actually going? And it's trying to go north at 300 miles an hour, but it's got this crosswind at 40 miles an hour, and so maybe I want to compute something which we call true velocity, called W, and it's going to end up being u plus v. The vector addition is going to allow me to do it. So 0I plus 300j plus 20 root 3I plus 20j. I'm left with 20 root 3I plus 320j. Now that's going to tell me the vector that's describing this motion of the plane. If I really just want to know how fast it's going, well, we've got our W. Let's compute the magnitude of W. The length of that vector should tell me the actual speed of the airplane. If we go through and calculate that, it's going to be the square root of 20 root 3 squared plus 320 squared. We get about 335 miles per hour. So even with this crosswind, it's still blowing enough in the right direction that the airplane is actually getting propelled by a little bit, as opposed to if it was going straight into it. And then the final thing we can compute is the true direction. So for this W, if I really want to know what the angle theta is, we'll go back to our original drawing. So I've got my blue line representing the direction of the airplane it was trying to go, and I'm probably going to get something like this for the actual vector that's telling me I know how fast it's going, but what's the actual direction? I'm going to need to compute an angle theta for that. But from what we saw earlier, we should be able to get that 320 over 20 root 3 is equal to the tangent of theta, which leaves us with theta is about 83.8 degrees. So we were right. We're moving not quite vertical, not quite up at 90 degrees or at pi over 2, but a little bit off there, being blown off to the side by the wind. But some of the force of the wind, while it's going this way, it's going to have parts of it going that way, parts of it going that way. It is going to help, and we'll see some of that up in the next section. There's a lot of techniques that can be used in vector algebra to work with this. We're only going to see a few of them here, but we can already see from this sort of thing the vector representation that we had here for the speed and direction of the plane, the speed and direction of the wind, a way to get the actual velocity, the actual speed, and figure out what direction the plane's really going.